brain-computer interfaces, called BCI, are devices that allow humans to use only their brains to communicate with their environment. Athena is a research team that works on functional and structural neuroimaging. Their purpose is to use non-invasive functional imaging using electroencephalography, EEG, in order to extract information that could be relevant to control BCI.
There can be many different types of BCI. For example, to command a cursor or a movement, a robotic hand, for example, or to select between different choices, all using only brain activity. One example of a BCI that we've been working on is called the P300 Speller. It allows a user to spell words using a keyboard which is on a screen and which flashes. And the fact that it flashes induces certain brain activities when the letter that the person wants to spell is flashed.
We ask the user to concentrate on the number of times a letter will flash. So it selects a letter, it counts the number of flashes, and from the brain signals, we are able to induce what letter the user has focused on.
So the P300 response is called P300 because it occurs 300 milliseconds approximately after an event which the person is very interested in. For example, if you're at a red light and you're waiting for the green light, as soon as the green light comes, you'll get a P300 response. So we're using this effect to measure in the electroencephalogram at which time there is P300 response, and using this information we can find which letter the person wants to spell.
Each person has his own peculiar P300 response. Before using it, the system needs to be calibrated. It consists in typing a word known both by the user and by the system in order to recognize how the new P300 response appears on the EEG.
This is important to have labeled data on which we know which are the flashes that contain the letter he wants to spell. These are target flashes, and which are the parts of the data that correspond to flashes and which there wasn't the letter he wants to spell. These are non-target flashes. So we have data with the labels. We know that such and such piece of EEG corresponds to target and such corresponds to non-target. And once we have these two types of data, we're going to look for features inside the data that separates these classes, that are specific of each class, that then will allow us to classify new data when there are no labels. After a certain number of flashes, the individual probabilities of each letter are going to evolve, thanks to all this new information that we get at each flash, and we will stop the flashes as soon as one letter has a much higher probability than the rest. And this is the letter that the person wanted to type.
For people suffering from severe disabilities, especially patients with a locked-in syndrome, there is a strong demand around communication devices. The Athena team was approached by the Nice University Hospital, and a prototype of the P300 Speller was tested there in a clinical study.
We have tested this system with the help of the hospital of Nice for 20 patients affected with a severe disability called ALS. The feedback has been very, very positive. One of our first users spelled the word j'adore. I liked it a lot. Some other were willing to keep the system with themselves or to find ways to buy it immediately. And we are not totally ready to do that. There is also a user in Chambéry who decided by himself, he contacted us, he saw that we were doing that. And he contacted us to be able to test it with a low-cost EEG system like the one you see behind us. And with the help of some computer engineer, he was able to set it up, and he had some success, and he was very helpful for us to try to make some advertising around the system and to help us finding some funding.
Notre étude en fait a montré qu'il y avait une excellente
And our study has showed that there was an excellent acceptability from patients of such a system, despite the technical difficulties that we still encounter today and which we hope to solve tomorrow. Finally, the patients were ready to try and use this type of system. So there really is a demand and a strong patient acceptability that is almost surprising regarding to their disabilities. Nevertheless, if we want to remain relatively simple and practical, there is ethics questions about how we can afford these new technologies. This type of question arises already with high-tech technology for communication, which are marketed and which are quite expensive. But for which patients, and how much should it cost? It's true that we cannot spare an economic reflection concerning all these new technologies that are developing. Today, patients need a system which is accessible to non-tech people, easy to use without any calibration phase, wireless in order to be easily used anywhere, low cost to be accessible to as many people as possible, and open source to be compatible with the most common softwares. Of course, technical points still need to be solved, but one of the crucial subjects for today is awareness of our own cerebral signal.
We want the end user, the user of a BCI, to be able to control their brain signals. So there is some awareness, self-awareness of brain signals that has to be brought to the user. And this is still a subject of research. In brain pathologies, such as attention deficit disorders or even epilepsy, if people can be shown their brain activity and maybe taught about their brain activity and taught to control their brain activity when it is not going right, then it can bring huge advances that were never envisioned yet.